Good morning, students. Myself, Dr. Shantani Bhattacharya, Assistant Professor of ECE Department, SRM Institute of Science and Technology, Cotton Clothu, Chennai. Today, I am going to start a new topic of digital logic design. There is actually I am including actually three topic: ring counter, Johnson counter, and also modern counter. Details of counter already I have described in counter video. So if you have any problem, then go and watch this video and start then this video. Okay. So first of all, ring counter. So what is ring counter? Ring counter is very simple. It is actually here you can see the this is the basics of the counter. Here all the D flip-flops are used. This is actually the 6-bit counter. You can use any bit of counter, 3-bit, 4-bit. Okay. So here as an example I have given you 6-bit counter. Okay. So this is D1 is the higher order bit, D6 is the lower order bit. Okay. Now you know that clock is very important for the counter. So here this is synchronous counter. Synchronous actually clock pulse is used where all the flip-flops are simultaneously actually works on the clock. Okay, that means clocks are simultaneously used in all the flip-flops. Okay. But in the case of ring counter, the main important part is that the Q of the D6. Okay, so that means output of D6. That means last flip flop's output D6 is connected to the first flip flop input. Okay, so first of all you can see this is my first bit. Okay, that means 1 0 0 0 0 0. This is 6-bit. I have started with this bit. Next clock pulse, what will happen? This is the 6, that means D6 is actually 0. This 0 will come to this input, to this first flip-flop input. Now what will happen? You can see this is the D6 output. So this 0 will come at this D1 position. Okay. So then what will happen, this 1 will shift to D2, then this 0 will shift to here, and in this way all other bits shifts. Okay, then after that again 0 will come here. Okay, so again this 0 will come here. Okay, and this 0 shift here, and this 1 shift in the bit D3, and then this D3 bit, previously it was 0, so now it is D4. Okay, in this way shift. Okay, again in the fourth clock pulse, what will happen? In the third clock pulse, D6 is actually 0. Then again in the fourth, starting on the fourth clock pulse, this 0 will come again to actually D1. That means this is actually the output of the sixth that means flip flop. Okay, then this will come here. Okay, D1. Okay, so then again one by one it shifts. So in this way, when this process continues up to when full actually this one whatever it is started, this one will come here in the D6 position. Again in the next clock pulse, this one will come in the D1 position. Okay, again the clock pulse due to the continuous clock pulse, again same process will go on. Okay, so this is a ring counter, and Johnson counter is similar to the ring counter. The difference is here Q, actually Q is not connected to the first flip flop. That means last, here actually 4 flip flops are used. Here you can see that complement of the fourth flip flop output is connected to the input of the first flip flop. Here also same clock pulse simultaneously used for all flip-flops. Without any clock pulse, the flip-flops are not actually worked. So here actually complemented output of the last flip-flop is actually the input of the first flip-flop. But in the case of ring counter, you can see here actually the original output is actually connected to the input of the first flip-flop. That means original output of the last flip-flop is connected to the input of the first flip-flop. But in the case of Johnson counter, what will happen? Actually here complemented output of the last flip-flop, that means Q4 bar, is connected to the input of the first flip-flop, that means D1. Then what will happen? That is here first it is 0 0 0 0, then this 0 this is the starting position, then this 0 is now it will actually complement. Okay, so we have to give the in the first input we have to give what we have to give. This is a complemented form, that means 0, that means 1, then again shift, then others are just shifted 0 0 0, then again this Q4 is the original output, then this original output will go to the this. Okay, that means this is the complemented output. This is 0, that means 1 will come here. Okay, and this 1 will shift here, then others are shifted also, then again 0, then 0's complement is 1, then 1, and these other two ones are just shifted. This is last. Okay, then in this way continuously this process continue up to all flip-flops output will be 0 0 0 0. So this is the Johnson counter principle. Okay, main the difference is ring counter and Johnson counter is, in the case of ring counter, the output of the original output of the last flip-flop is actually goes to the input of the first flip-flop. But in the case of Johnson counter, what will happen? The complemented output of the last flip-flop will actually go to the input of the first flip-flop. Okay, now coming to the mod n counter. Okay, so this is very important. Mod n counter is actually, that means how you actually design any type of counter number. N means that means how many steps you can count. Mod n means we can count, we can say mod 4 counter, mod 5 counter, mod 6 counter. Here this is actually the diagram of the mod 5 counter. Okay, so what is the design process? Okay, what is the design process? So to describe this design process, so what is actually here going on? Okay, so actually first of all this is actually asynchronous mod n counter. How I can understand this is asynchronous? You can see that clock pulse is only applied, that means original clock pulse is only applied to the first flip-flop. Okay, and the output of the previous flip-flop, that means output of the first flip-flop is connected to the in clock pulse as a next flip-flop, and also output of the second flip-flop is connected as a clock pulse of the third flip-flop. Okay, and here J and K both are connected to VCC, and all J and K are connected to VCC. So it is actually why J and K are connected to VCC? Because we know in the case of JK flip-flop, when we connect J and K both 1 and 1, then applying clock, it will continuously toggle. Okay, so here we have taken the Q0, Q1 and Q2 output. Okay, now what is this part? Okay, what is this part? There is a NAND gate. So now I am actually describing how to design the modern clock pulse. So for this purpose you have to know, so for first of all, in the case of mod n, n is actually stands for number of steps. Okay, that means here it is a I am designing here the mod 5 counter. Okay, so that means how many steps we have to count? That means 5. So we have to count here 0 0 0 0 0 1 0 1 0, then 0 1 1, then 1 0 0 and 1 0 1. So this is 0, this is decimal number 1, decimal number 2, decimal number 3, 4 and 5. Here first of all, to design this modern counter we have to select first step is step number this is step number 1 is how many flip-flops we have to use. So there is some equation that 2 to the power n minus 1 less than equals to n less than equals to 2 to the power n. n is actually number of flip-flops. Okay, number of flip-flops. Okay, so here we have to design the mod 5 counter. Okay, so mod 5 counter, that means 2 to the power this is if we consider n equals to, now we are considering n equals to 3. Okay, so just you can one by one you have to consider. Okay, so I know this is we have to use basically 3. So one example I have given you 3, that means 3 minus 1, it is actually 2. Okay, that means 2 less than 2 to the power 3. That means if I again write 2 to the power 2 less than equals to n less than equals to 2 to the power 3. So what will come here? That means 4 less than equals to 5 less than equals to 8. This is actually we have to design mod 5 counter. So if I use that means 2 to the power 4 means if I use only 2 flip-flops, then only I count up to mod 4. Okay, so we cannot count mod 5 actually. So we have to use this, that means 3 flip-flops we have to use. Okay, so here basically we use here flip-flop number 1 2 3 flip-flops. Why we use 3 flip-flops here, I think all of you clear now, because if we use 2 flip-flops, number of 2, so we cannot count mod 5. Okay, so, or we cannot count 5. Okay, so this is the first step, that means we have to use 3 flip-flops. Okay, and then what will happen here? So first of all, here in the case of mod 5 counter, the main thing is we have to count 0 0 0 0 0 1 0 1 0 0 1 1 then 1 0 0, but mod 5 counter, but we will not count 1 0 1. Okay, so that means it will start from if I use this page, that means it will start from 0 0 0, then 0 0 1, then 0 1 0, then 0 1 1, then it will count 1 0 0, then again it will come 0 0, it will count 0 0 0. Here after 4 it will definitely come 1 0 1, that means 5, but we will skip this 5 and from 4 we will again count 0 0 0. So this is the main thing for mod 5 counter. So or if you choose mod 8, okay, so in that case how many number of flip-flops you have to use? First step 1 you have to use flip-flop, that means 2 to the power, if I this is n, this is n, this is 2 to the power, this is actually 2 to the power if I count 3 here. Okay, and also 3 minus 2, that means 3 minus 1 equals to 2. That means here we have to count 8, that means 2 to the power 4 less than, that is equal, this is actually equals to 8, it is 8. That means here also we have to use, if I use 3 flip-flops, we can also count mod n counter. That means if I use flip-flop 3, we can count up to mod 8 counter. Okay, after that if I choose mod 9, then we have to increase this flip-flop number. We have to go to 4 flip-flop. Okay, so for mod 16 we have to go to the 4 to the power 4. Okay, now in the case of mod 8, what will happen? 0 0 0 0, as it is a 4-bit number, then we have to count 0 0 0 1, then 0 0 1 0, then 0 0 1 1, then this is 0 1 0 0, then 5 0 1 0 1, after that 0 4 1, this is 6, after that this is 7, then we will skip, there is a, after that it will come 8, then again 0 0 0 0, but we will skip this 8. Okay, we will skip this 8, and from 7 we will directly go to the 0. Okay, so this is the process. So again I just repeat once again. So to design a mod n counter, I have given you the example of mod 5, and I also have given you the example, I have already show you the example of mod 8. So in the case of mod 5 counter, you have to count 0 1 2 3 4 5, sorry, 0 1 2 3 4, then there is a 5 will come, but we don't count 5. Directly after 4 we have to count 0. So what is the process? I will show you. First of all, this is the main thing that you have to understand, that in the case of mod 5 counter, we are telling mod 5, but we have to count from 0 to 4. That means you can see that there is actually 5 number is also already there, 1 2 3 4 5. Okay, so 0 to 4 we will count, and 5 number we will skip, and again from 4 to we will go from 4 to 0. So first step for this purpose is number of, how many number of flip-flops we basically need to design the mod 5 counter or any mod counter. Okay, so what is the equation? 2 to the power n minus 1 less than equals to n less than equals to the power n. N is actually the number of flip-flops, and capital N is actually mod number. Okay, so here we consider for mod 5 counter 2 to the power 3, and this is 3 minus 1 2 to the power 2, so it will come 4 less than is equal to 5 less than is equal to 8. So if I choose number of flip-flop 2, so we can count up to 4. We cannot design mod 5 counter. Okay, so we have to take mod we have to take actually 3 flip-flops. Okay, so now we will tell basically how we will skip 101 position and how we will go from 100 to 000. Okay, so here you can see that when after this fourth number will come, then again come, it will 101, but you can see the bit number 1 and bit number 3, if I write 0 and 0, then it will go, then definitely it will go 0. That means we have to actually design in such a way that this 1 will be 0 and this one also will be 0. So what we will do, basically this bit this is actually the position number 1, Q0, and Q2 output we will take. In that condition, when 5 count will come, then these two output, that means Q0 output will come here 1 and Q2 output also at that position 1. But Q, when it is a more, when 5, it is at that moment it is the position number 5, 1 0 1, but we will not count this 101. Okay, so this 1 I will take and this 1 I will also take. Okay, and all of you know, if both the inputs of the or all the inputs of the NAND gate if 1, then output goes 0. So after this output of the NAND gate, we will actually connect this clear button. Clear button means, that means all flip-flop will be 0 0 0. That means after when we will count 1 2 3 4 5, then it will also come 101 this stage, okay. But we will at that when it will come this stage, then we will actually within a very few seconds, this process is very fast, okay. So when this stage will come, this actually 5 number will come, then quickly this 1 will come here, and that means this first bit and last bit will come here, and it will go 0, and this output of the NAND gate will clear. So that means output will again show 0 0 0. So very small amount of time we can see the this value also, but in this way we can actually avoid the 0 0 101 condition, okay. So this is the design of the mod n counter. I hope all of you can understand. If you have any doubt, then you definitely give me a message in a comment section, and thank you, and keep watching my video. Thank you so much.